So, let us do this third normalization. This is one result in commutative algebra which is quite important in the geometric point of view as well. Let me just try to explain the vaguely explain the geometric situation. So, suppose you are you have an algebraic set in Kn. K is a field. So, we call this affine space. You must have already done the exercises in Atia MacDonald that affines the Kn with Zariski topology is usually denoted by A and K, and this is called affine space. So, if you have an algebraic, if you have a subset X of Kn, then I can define this ideal I of x to be set of all f x1 up to xn in k x1 up to xn, such that f of a1 up to an is 0 for all a1 up to an in x. Okay. Then this is an ideal in kx1 up to xn. Okay. The ring Ax, usually denoted by Ax, k x1 up to xn modulo I of x is called the coordinate ring of the algebraic set X. Okay. So, the idea of the Noether normalization is the following. Suppose you have an algebraic set X, okay, in some A and K. The question is whether we do have a projection onto A R K. So, suppose I have a projection like this. Suppose I have a map between suppose I have a surjective map like this, then I have an injection from, so I have an injection from K, let us say some Z1 up to ZR to the coordinate ring A of x. So, this is injective map. What does this, if I have a projection like this, then I have a map like this. What we are looking for in geometry, what one looks for is, can we have a projection like this so that this becomes a finite extension, Ax become a finite extension of this polynomial ring. Once you have, this is a polynomial ring and this is a finite extension. Z1 up to ZR. So, if I have a map from X to AR, AKR, then correspondingly I have, so this will be the coordinate ring of this. because you have only the 0 polynomial that. So, if I have a map from x from k x1 sorry a n k to y in a m k. Okay. If I have a morphism like this, what I mean, there is something called morphism, then correspondingly I have a map between the coordinate rings of y and x. That is what we have here. This is the coordinate ring of this variety, because there is only 0 polynomial that vanishes at all points of this. So, this is polynomial ring modulo the 0 ideal. So, the question here is whether we can have such a projection so that this becomes a finite extension. It so turns out that it need not always be the case. We need not always have such a projection giving something like this always. For example, if you take, so let us take k equal to r, x equal to the 0 set of all x1 x2, so that x1 x2 is 1. It is basically this set. Okay. Now, if I look at this as my r equal to 1, if I take the projection, okay, I will miss the point 0. Accordingly, if I look at correspondingly, if I have c x1, I have c x1 to not c, okay, it does not really, r x1 x2 x1 x2 minus 1, this is the coordinate ring of this variety, right. I have this map. Now, this is, I do not have, see, if I look at the ideal generated by x1 here, this is a prime ideal here. There is no prime ideal here that is lying over x1. Okay. So, therefore, this does not become a finite extension. Now, we do a small trick here, everything remains the same. I do a twist here, I just change my axis, instead of the standard axis, I change my axis to take y1 equal to x1 plus x2 and y2 equal to x1 minus x2. So, when I make this transformation, the variety becomes like this. So, what we are doing is we are just twisting 45 degrees, right. This becomes the axis becomes these two lines. Sorry, so I am denote no, is this correct? Yeah. oh, at 1 not 0. So, this is like this. At 1 it comes twisted by 45 degrees, because what happens when what is x1? X1 is y1 plus y2 by 2, and x2 is y1 minus y2 by 2, right. So, the axis, this is this line and the other one is this line. So, it is basically 45 degree. So, you become, and the variety becomes this. There is no change as such for the variety, only thing is we are looking at in a different angle. Once we twist this, now what happens to the variety now? So, we are now in R y1 y2, and what is, so let us call this to be the new variety to be A of y. A of y, the coordinate ring of A of y becomes, this becomes y1 y2. So, if I take x1 x2 to be x1 x2 the product, right, this becomes y1 square minus y2 square 4. Now, this is, see, y1 square. So, if I can take, let us say I can send R y1 now y1 y2 is integral over this ring, y2 is integral over this ring, no, not this one, right, because it satisfies the polynomial t square minus y1 square minus 4, y1 bar square minus 4. So, over this ring also y2 is integral. So, what we have is, this is a finite extension now, because it is generated by y1 y2, I mean this becomes a finite extension because it is generated by y1 y2 sorry 1 y2 and y1 y2. After that you can create y2 square is y1 square minus 4. So, this gives me a method of getting a finitely generated K algebra as a finite module over a polynomial ring. Now, this the number that appears here, or the numbers that appears here, this is called dimension of the variety. It's not defined by this way, but it turns out to be that this becomes what is called dimension of a given variety. So, the idea is this. Let's see, let's try to prove this. So, first let me make the statement. Let R be a finitely generated K algebra then there exists variables z1, z2 up to zr such that k so with an injective homomorphism from k z1 up to zr to r such that so let me call this S. R is a finitely generated S module. Maybe which makes so here I will do the proof assuming that the field is infinite. When the proof is when the field is finite, the proof is slightly more complicated, and I will leave it to you to read it on your own. Okay. It is not very different or too difficult, but it is slightly more lengthy. It uses some more intricate arguments, but I will leave it to you to learn it yourself. The proof for theorem when the field is infinite is not very difficult as well. So, there are only I mean very few changes that are required for the proof to be valid in the case of finite fields, but that lemma one needs to be careful in proving. So, let us prove the theorem for the case of infinite fields. So, first let R be, and it is a finitely generated K algebra. So, I can write R as some x1 up to xn. We prove the theorem by induction on n. If n is 0, R is k, we can take R small r to be 0 itself, everything works. Then take R to be 0 itself, that works. Now, suppose n is positive. Now, let us assume by induction that if I have a finitely generated K algebra, generated by less than or equal to n minus 1 elements, then I can find some z1 up to zr, so that this becomes a inclusion and R becomes a finitely generated S module. Okay. So, let us write down the induction hypothesis. If R is a finitely generated K algebra generated by n minus 1 at most n minus 1 elements, then there exists z1 up to z, let us write R prime such that there exist variables k z1 up to z r prime to r is injective and r is, so call this S prime, is a finitely generated S prime module. Now, the idea is to prove by induction. So, the idea is to bring it down to the case of n minus 1, a case of a finitely generated K algebra having n minus 1 generators. Okay. So, let us look at the situation we have now. Let R be equal to k x 1 to x n. See, if all these x 1 up to x n, they are all algebraically independent, then we can take n to be R itself. That is, there are no polynomial f that vanishes on all the, no polynomial f such that f of x 1 up to x n is 0. They themselves are variables. If x 1 up to x n all of them are variables, then we do not really have to worry, we can just take n to be R itself. Okay. So, if for any f let us say polynomials in k x 1 up to x n, f of x 1 up to x n is non-zero for any non-zero polynomial, then take n r equal to n and z I equal to x I. We are through. This itself is a polynomial ring. There are no polynomial relations among x 1 up to x n, which means this itself is a polynomial ring. They are all algebraically independent. See, here there is a relation between y 1 and y 2, right. That is y 1 square minus y 2 square minus 4 is 0 in on this ring. So, this I can write this as R y 1 bar y 2 bar, but in this one y 1 alone does not have a relation, but y 2 has y 1 y 2 satisfies a relation. What is that? Y 1 square minus y 2 square is 4. So, therefore, this is, these two are not algebraically independent. If I take the polynomial x 1 square minus x 2 square minus 4 and put y 1 equal to x 1, x 1 equal to y 1 bar and y 2 equal to x 2 bar, this becomes 0. Okay. If we do not have any such situation that x 1 and x 2 are no way related, not only linear relation, no order relation, no higher order relation, that is, there are no polynomials satisfying x 1 up to x n, then you can take, then that what that says is that all of them are variables, they are all algebraically independent. So, there are, I can take z n r to be n and each z I to be x I. So, in this case we are through. So, suppose there exists f x 1 up to x n non-zero polynomial such that f of x 1 up to x n is 0. Suppose this is 0. Now, see, as in the case of this example that we discussed, can we, the idea is again, the idea is to bring this down to a case like this. I have R, I want to bring it down to a situation like this. x1 up to xn minus 1, where this is finite. Once you have this situation, then by induction I can say that I have a k z1 up to zr, polynomial ring k z1 up to zr, such that this is finite. Now, if this is finite and this is finite, this is a finite module over this ring and this is a finite module over this ring, then R is a finite module over this ring. We are through. Okay. But then we need to make sure that I can have a finite integral extension like this. But then as we saw in the earlier case, for example, in the case of R x1 x2 modulo x1 x2 minus 1, in this case neither x1 nor x2 is integral over this. See, if I look at the ring R x1 bar, then x2 bar is not, so let me call this R x1 bar x2 bar. Then this is not integral, x2 bar is not integral over this, because the polynomial that you are considering is not monic, right. This is not monic polynomial. So, this extension is not integral. If this is integral, if you take this, if this is integral, then given any ideal, prime ideal here, I will have a prime ideal here containing the given prime ideal. But if I look at the, this is a prime ideal here, right, but then I do not have a prime ideal here containing x1 bar. If it contains x1 bar, it will become the whole ring. So, there are no prime ideals here which contains this one. So, therefore, this is not an integral extension. So, if I simply take some variables, that might not work. So, we what we did here was we twisted the axis. Okay. Similarly, we can try to twist the axis and try to see if we can get an integral extension. So, let us see how we can do this. Now, I have a polynomial such that this is 0. So, the question is whether we can make a twist so that one of the variable has leading coefficient 1. Again, look at the example that we did. We made x1 equal to y1 plus y2 and x2 equal to y1 minus y2, or the other way around. And then when we substituted, one of the variables became y1 became monic, I mean the leading coefficient of y1 became monic, right. So, over C y2 it became an integral extension. So, therefore, in this case the question is whether we can indeed do this twist. So, let us see how we can do that. Let us write f of x1 up to xn as a polynomial. So, let degree of this let f1 let us write like this, f b x1 up to xn where f I is the homogeneous component of degree I. Do you understand this? The homogeneous component means the terms of degree I. So, if I take the x1 square plus x1 x2 cube plus x2 power 4, this is degree 4 component, this is f4, this is f2. Okay. I collect all the terms of same degree and write this as fi. So, if we have to tweak the polynomial and get a monic polynomial, we only have to worry about this one, right. Once we tweak the highest degree term and make one of the coefficients, one of the leading the coefficients of one of them monic, then we can take that polynomial if we can make a linear change. So, so the question is whether we can deal with this homogeneous polynomial and make corresponding change. So, consider the polynomial So, let us write this as summation C k1 up to kn x1 power k1 to xn power kn summation ki is equal to d. I am just representing the polynomial, they are all of degree d. Okay. What happens to this polynomial if I make a linear change? Okay. For example, suppose let xi be equal to yi plus ai yn. Okay. Let me just write this as yi times xi equal to yi times ai plus n. Yi's are, again I am just say I am taking yi's so that this is this for some ai's, n minus 1, okay, for and xn equal to yn. Let us just substitute like this. What do you get? fd y1 up to yn. So, each one will become x1 will be y1 plus a1 yn whole power k1 and so on. Suppose I write this as a polynomial in yn with coefficients coming from other, as a polynomial in yn with coefficients coming from k y1 up to yn minus 1. What would be the highest degree highest degree will be k1, I mean the summation, the degree is d, right. So, the highest degree will be y n power d, okay. Now, what would be the y n power d plus, I would just write the coefficients as I will just write this O y n power d minus 1, something less than or equal to, I mean with coefficients coming from y1 k y1 up to y n. Now, what would be the leading coefficient here? There would be, see I am substituting x1 by this one. So, see from each of them, see I am writing y1 plus a1 y n whole power k1 y n minus 1 plus a n minus 1 y n whole power k n minus 1 y n whole power k n. I am looking at k1, see this is one term, right, this is C k1 up to k n term. In each term I will have a1 power k1 up to a n minus 1 power k n minus 1 times 1 multiplied by y n power k, I mean y n power d, right. So, the leading term, and this will come from each C1 I mean each term like this. So, the leading coefficient will be of the form C k1 up to k n, a1 power k1, a2 power k2 up to a n minus 1 power k n minus 1 and 1 coming from here. From each term that will be there, and y n power d will be common to each of them. So, therefore, this is nothing but, so okay, let me just write it like this, a1 power k1 up to a n minus 1 power k n minus 1 1 power k n. I will write it like this. This will be the coefficient of y n power d. But now, what is this? This is nothing but f d of a1 to a n minus 1 1 y n power d terms which are less than. So, the question here, can we make a change? See here I have obtained a polynomial such that this is 0. I have obtained a relation whose f is 0. Now, this is 0 means if I multiply by any lambda in k, this will also be 0. So, if I can get a polynomial whose leading coefficient is an element from k, I can always scale it. So, here I have an element from k, but now what is that I need to say here? See, if I can choose a1 up to a n minus 1, so that given this homogeneous polynomial, I can always choose a1 up to a n minus 1, so that this becomes non-zero. There exists a1 up to a n minus 1, so that this is non-zero. If I can say that, then this transformation will give me a new polynomial. So, I make this transformation the entire thing, and this will be degree d this will have yn power d with some coefficients in k, which I can always scale it, and some other terms whose degree is as a power of n, it will as a polynomial in yn, they will have smaller degrees, and that will imply that, and this if you put f of x1 up to xn, again this will become 0, this new polynomial will again become 0, because they are all x1 coming from this itself. So that will become 0, that will imply that yn is integral over k y1 up to yn minus 1. Now you can apply induction on k y1 up to yn minus 1, get a polynomial ring which injects into y1 up to yn minus 1. This is integral will imply that this is finite, this is by induction this is finite, therefore this is finite. That is the idea. So the question is whether given a homogeneous polynomial, can we always find some a1 up to an minus 1 so that this becomes non-zero. Okay. See, in the case of infinite fields, this is at least intuitively you can say that it should be possible. I mean, you can if you look at a polynomial and look at its solutions in the n space, that should be a closed set, which is so we should always be able to pick a point outside the given closed set, but we have to prove that. But when your field is finite, it is much more difficult. For example, there can exist polynomials which is as a polynomial it is non-zero, but you put any value of the field it becomes 0. For example, x power p power n minus 1, x power p power n minus 1 minus 1, or x power p minus 1 minus 1, that becomes, that is a non-zero polynomial such that for every a in the in fp this is 0, right. So therefore when the field is finite it is little tricky, one has to deal it separately, but when your field is infinite, what I claim is the following: let g x1 up to xn in, so let me use a different notation, g t1 up to tn in the polynomial ring is be a homogeneous polynomial, then there exists a1 up to a minus 1 in k such that g a1 up to an minus 1 1 is non-zero. That is precisely what we want to prove here. Okay. So again we prove this by induction. If n is equal to 1, we are through. Take any non-zero. So this is g is a degree 1 degree some this x power n. So if n is 1, then g t1 is some alpha t1 power r for some r, because it is homogeneous polynomial. Then take a1 to be any non-zero element in K. So, the claim is true if n is 1. Now, suppose assume that assume the induction hypothesis that if I have a homogeneous polynomial of degree n minus 1, then it has a non-zero root like this. Sorry, n minus 1 elements is with this being non-zero. So, let f sorry so 1 itself a1 take a1 there is no a1 that is true then g of 1 is non-zero, g of 1 is alpha which is non-zero. So, let now assume that suppose n is positive, write g t1 up to tn as summation g I t1 up to tn minus 1 t2 up to tn t1 power I from 1 to d. So, write this as a polynomial in t1 power polynomial in t1 with coefficients coming from t2 up to tn. Okay. Since g is non-zero, there exists one I such that at least one I such that g I is non-zero. G I is a non-zero polynomial. By induction, there exists a2 up to n minus 1 in k such that, so let us say g I a2 up to n minus 1 is non-zero. For this of course, it will be homogeneous, because this is, if I take a term of degree the g is homogeneous. So, if I take t1 power I, the rest of the terms, each of the terms will have degree I minus 1, g I will be of degree the rest d minus I, degree of g I will precisely be d minus I if I assume degree of this is d. Okay. So, now for this corresponding I have g I is non-zero. Now, what I do is I look at, consider the polynomial g of t1 a2 up to an minus 1 1. This is a polynomial, non-zero polynomial in k t1 k t1, because this term is non-zero. Now, this is a non-zero polynomial here, therefore, there exists at least k is infinite, there exists at least an a1 in k such that g a1 a2 to an minus 1 is non-zero, and that is precisely what we want to do. Okay. So, once we obtain this, what we have is, let's go back. I take this f this is 0. Okay. Now, if I substitute x 1 instead of x 1, I just take this a 1 up to a n minus 1 and put x I equal to this equation. That will give me, this will give me, I mean if I put x I equal to this, that will give me another say g y 1 up to y n, but g y 1 up to y n will again be 0, but then it will have a y n will have a leading coefficient coming from the field, which I can always scale it. That will say that y n is integral, this says that y n is integral over k y 1 up to y n minus 1. By induction, k there exists z 1 up to z r such that k z 1 up to z r, this is y 1 up to y n minus 1, this is finite, and this is, since y n is integral y 1 up to y n minus 1, this is also finite. Is finite. Now, this is finite, this to this is finite, therefore, this to this is finite. But what are the substitutions that we had made? X 1 equal to y 1 plus a 1 y n, x 2 equal to y 2 plus a 2 y n, and so on up to y n. So, therefore, this ring is same as, note that k y 1 up to y n is same as k x 1 up to x n. So, that finishes the proof. X n is y n. Therefore, now x n minus 1 is y n minus 1 plus a n minus 1 y n. So, this is x n, right. So, x n is here, therefore, y n minus 1 is here, I mean y n minus 1 is here. So, therefore, x 1 minus 1 is here. Now, keep going back, what you get is, this is certainly contained here, but this is also contained here, therefore, they are equal. That means, I have obtained z 1 up to z r such that this contained in k x 1 up to x n is a finite extension. That is precisely what the Noether normalization lemma says. We will do some applications of Noether normalization in the next class.